In the previous video, we studied conservation of mass and the application of the Reynolds transport theorem to conservation of mass, and we derived what equation, and we did an example of conservation of mass. Now, in this video, we're going to be looking at linear momentum equation and how we can derive it also from the Reynolds transport theorem. So for linear momentum, we're going to be saying that B is equal to mass times velocity, and that beta, remember, is just the term dB over dm, which in our case is going to be dmv over dm, which we can simplify as just the velocity, because we see that dmv over dm, the dm's would cancel and we'd be left with just velocity. And so in our most general sense of the equation, we can start with a deformable control volume just to keep it the most complex possible, and then we'll simplify it later. We can say that d mv dt for the system is equal to, so the differential of mv with the system is actually equal to the sum of the forces. Okay, so we actually know that this term is essentially equal to the sum of the forces, because force is equal to ma. If we have a constant mass in our system, or a mass that is not differentiated, we have df, we essentially have the sum of the forces in the system. So that's the first important point we can make. And this is equal to the right side of the equation that we're going to write out right now. So the most general term of the equation would be d dt times the integral of control volume v times rho dv. Okay, so make sure you make the distinction between volume and velocity. Okay, we're using velocity as beta, so we have velocity in that term, plus the integral along the control surface of velocity times rho times v r. Okay, so that's v relative that we described in video 1 times n dA. Okay, so we have this general equation. And this term right here could be separated into two terms for the terms out and in. Okay, the out terms would be positive, the in terms would be negative, but we'll look at how we can break that down a little bit later. Okay, so this would be out and in combined. Okay, but we can definitely look at it in separate terms later on. So some important points about this equation and about what we've done just here. So important points. The first important point we can make is that v is the velocity of the fluid relative to an inertial coordinate system. So v is a velocity that is the fluid velocity relative to an inertial coordinate system. So a coordinate system that does not move. Okay. Number 2 is that the sum of the forces are the forces on the system. Okay, and that's usually called free body forces. Okay, those forces are on the system. Okay, and number 3, that the equation, and we can say even that the entire equation, is a vector relation and we can say that V essentially has direction. So velocity has direction, and the direction of velocity is very important. And so we have to try and simplify this problem a little bit just to make sure that we understand what's happening. And doing the sum of the forces in all directions is usually something very complicated to do. So if we look at our equation, it's the sum of the forces in all directions is equal to this equation that is a complete equation. Now, in order to make it easier, we can use different terms for different directions, and we're actually going to come up with a system of equations with 3 different directions instead of just one. So we're going to be looking at 3 different directions instead of just one direction to make it easier for us to solve problems. So the first direction we can say is we could use the x direction. And if we use the x direction, we can say that Vx is equal to little u. Okay, if we were to use the y direction, we could say that Vy is equal to little v, and we can say that Vz is equal to, so the velocity in the z direction would be equal to a little w. Okay, so that's just convention that they use in fluid mechanics. Now, once we have that set up, we can say, let's look at the sum of the forces in x. So the sum of the forces in x is equal to d dt times the integral of u rho dv plus the integral on the control surface. So this first integral is on control volume, the second one is on control surface, is equal to u times rho times v relative dot n dA. Okay, we're keeping our equation as general as possible for now. And we can say the same thing, so we can do the sum of Fy with the terms with a little v, and the sum of Fz with the terms with a small w. Okay, now to simplify our problem, we can say that for a fixed control volume, we now can simplify our problem to say v relative is just equal to v. Okay, since the control volume is fixed, our Vs, or our V of our surface, is not moving anymore. Therefore, we can simplify our problem to the following general equation and also to our specific x, y, and z equations. So the sum of F for a fixed control volume would just be equal to d dt times the integral of V in all directions, rho dV, plus the integral, so this is for control volume, control surface, plus the integral of V rho times V dot N dA. Okay, and we're going to come up with new terms called the momentum and momentum flux. So we're going to call new terms. So we're going to look at what one dimension momentum flux means. So what it actually means. So we're going to look at one-dimensional momentum flux and how we can use that further along. So we're going to call momentum capital M, and momentum flux, so the flux of momentum is just going to be equal to m dot. Okay, capital M dot. Do not mix it up with mass m dot, okay? So we can say that m dot of the control surface is actually equal to the integral of CS v rho times velocity dot n dA. Okay, so essentially what we're doing is we're just calling this term the momentum flux. So this term can be called momentum flux. Okay, so it's the amount of momentum that crosses the boundary, essentially, through the control surface. Okay, now if we simplify this control surface and we say that the cross section is 1D, so if the cross section of the surface is one-dimensional, we can say that V and density are uniform across that surface. Okay, the velocity and the density across that surface are uniform. And so we can write that the momentum flux would be equal to a much simpler equation. So it would be equal to velocity multiplied by rho times Vn, okay, V normal, times AI, and that we know this is equal to m dot, and so that would be equal to m dot times velocity. And this would be the equation for outlet flow, essentially. So if we have a 1D outlet, we know that the momentum flux is equal to m dot times v, okay, mass flow rate times velocity. So we can rewrite our equation as the sum of the forces is equal to d dt times the integral of v rho dv, which is our rate of change in the control volume of our linear momentum, plus the sum of m dot I vi out minus the sum of m dot I vi in. Okay, and this is for however many exits and entrances there are. Okay, so we see that we can simplify our equation if our cross section is one-dimensional, and we can get a much simpler equation. Now, there's an extra little thing that we can do with this equation that makes it a lot easier to use in general when we're looking at pressure in a system and looking at what's happening in a pressure in a system. So I'm copying over a diagram that we have where we can see the pressure force on the system and how we can apply pressure to the force. So usually when we have linear momentum relations, when we have a control surface, we look at the pressure applied over the area, and that would be equal to our force. So we remember that if we have a uniform force, on a surface, we know that this force is equal to the negative pressure of area times the integral of dA. So the sum of the forces is essentially all the pressure around multiplied by the area. So if we look at this first diagram here, we have a closed control surface and we have a uniform pressure, applying a force around the system. Now, we can say that in this first condition, we have that the force due to pressure, okay, I'm going to call this F press, the force due to pressure is equal to the integral of control surface times P in the negative n direction times dA. Okay, we know that P, the pressure, is always in the negative n direction. It's negative to the normal, so it's always going to be at 90 degrees with the surface going inwards. Now, this is the case where we have pressure atmosphere all around. So that means that essentially our pressure is always going to be connected from all around. And if we have pressure all around, so F of uniform pressure, so this is our general equation when we look at pressure going outside from the outside. And if we look at pressure atmosphere all around, we can say that we have a force of uniform pressure. Okay, we have uniform pressure all around, which we can call FUP. And do not confuse that with force up. It's just FUP is equal to the integral of P atmosphere in the negative n direction times dA. And since pressure atmosphere is constant, we can take pressure atmosphere out of the system. So we have that minus P atmosphere times the integral of n dA. Okay, now if we do this integral and we look at atmospheric pressure on any body, what do we come out with this integral? So try to think about this problem. We actually get a value of 0. Why do we get a value of 0 for F uniform pressure? Well, if we have a uniform pressure around a system, essentially we do not feel the pressure. So we know that atmospheric pressure in the atmosphere is 101,325 pascals. Yet as human beings, we live every day with this pressure and we don't really feel it. We don't really feel the pressure from the atmosphere. The reason we don't feel this pressure from the atmosphere is you can think of us as a closed control surface. And all the atmospheric pressure is doing on our system is pushing, for example, on the left of our body, it's pushing us towards the right. And on the right of our body, it's pushing us towards the left. So actually, the sum of all the pressures is essentially equal to 0. So we do not feel atmospheric pressure. A control surface in the atmosphere does not feel any pressure from atmospheric. So that's a pretty interesting comment that we can make. And due to that, we can actually simplify our engineering problems in a certain way. So if we go back to our diagram above, in part B, we now have a non-uniform pressure. So let's say that now on your body, you have the pressure of atmosphere, and then you have wind hitting you from this direction, and this direction, and this wind or this person pushing you creates an extra pressure on you. Now, when that happens, you start feeling that pressure. So the absolute pressure you feel on that area, so on this area right here, or this area right here, the absolute pressure that you feel is the atmospheric pressure, which we don't really feel, plus the pressure gauge, or the pressure that is added in addition to the atmospheric pressure. So essentially what you're feeling is just a gauge pressure. You're just feeling this change in pressure due to the wind. The absolute pressure of that, you don't really feel the absolute because you don't feel the atmospheric. So what you feel is this. The total pressure is actually the absolute pressure. But what we feel, so as a human, if we have pressure on us, what we feel is this P gauge. Okay, because the atmospheric pressure is being canceled out throughout the system. So that means that the only pressure that we feel and the only pressure that a system feels in terms of a change are these three pressure gauges. These three pressures that are added to the system. So if we look at the bottom left system here, we can say that this little part here is P gauge, and this part from here to here would be P absolute. And the first part, the little part, only at the front would be P atmospheric. So hopefully that makes sense as to why we feel P gauge and not P atmospheric or P absolute. We don't feel P absolute because P atmospheric is canceled out by the rest of the atmosphere touching any other side of that control surface. So a control surface only feels the pressure from gauge, or the change in pressure that is being applied. And so we can write that whenever we have a different pressure than atmosphere, we can write that our force of pressure in our system is equal to the integral of the control surface of pressure minus P atmosphere. Okay, and our pressure is our total pressure in the minus n direction times dA. Okay, so our force of pressure that we feel in our system is always the absolute pressure minus the atmospheric pressure. And that means that we can sort of use a shortcut. If we know that we can measure gauge pressure and we know the gauge pressure, we can just write that P gauge, we can find the force of pressure with P gauge in the negative n direction times dA. So what this means is that if we have atmospheric pressure in a system where we have other pressures engaged to create momentum, we actually don't need to worry about the atmospheric pressure. We only worry about the gauge pressure. And it turns out that most of our measuring instruments do not measure absolute pressure. They just measure gauge pressure. They measure the difference between pressure absolute and pressure atmospheric, which is our gauge pressure. And our gauge pressure is really what we feel, because atmospheric essentially cancels out because it comes from every angle around our body or any control surface in itself. That's why we don't see any compression. We don't feel any compression from atmospheric pressure. Now, if someone starts pushing you, then you feel a compression from that side, and that would be a pressure gauge that you're feeling, not the absolute pressure. Okay, so I hope this is clear, and I really want to make this clear so that it's understood, but we're also going to be using it in example problems to sort of illustrate our point, and you'll be doing it in your study problems as well. So the next thing I want to do is to look at an example problem, which is example 3.7. So I'm going to copy over the diagrams for this one, and we're going to get started on this. So bear with me for a second while I copy over the terms. So we have a problem that says a fixed control volume of a stream tube in steady flow has a uniform inlet flow rho 1, A1, V1, and a uniform exit flow rho 2, A2, V2. And remember, the book does velocity differently. So this is a velocity term. Okay, I'm just going to add bars through it so that we don't get confused throughout our system. And we're told to find an expression for the net force on the control volume. And we're also given a little bit of a help with figure 3.7, which shows that we have a stream tube and steady flow and the vector diagram for computing the net force. Now, we're actually going to be looking at this and trying to figure out the net force. So the first thing we can do is we can write our general equation for this system. So we know that we have uniform inlet flow. So this is something that will help us understand what's happening. So the assumptions that we can make from this question are the following. So assumptions, we can assume that we have 1D flow. Okay, we're told we have uniform inlet flow, so we're going to assume that we have 1D flow. We also know that the flow is steady, which means that the flow is continual, and that means that there's no change within the control volume. And when there's no change within the control volume, we can make sort of an assumption. And what we're going to do too is we're going to define our control volume. So we know that this says fixed control volume, but it doesn't really show it. So let me just draw the control surface so that we have the control surface throughout this volume. And the interesting thing about this problem is that we have a bend. Okay, we have a bend in this problem, so we can't just do it in the x direction or do it in the y direction, but we'll see that it's actually pretty simple. Okay, we see that solving this problem is actually going to be pretty simple and pretty understandable. So we have 1D flow, we have steady flow, and now we can start solving the problem. So what we're going to do is, because we don't have a certain flow in only one direction, we're going to use a general equation, which is sum of F is equal to d dt times the integral of velocity over control volume times rho dv. And since we know that we have this steady flow, we can say that this term goes to 0. We have no change in the properties of velocity times mass inside the flow. So the mass flow rate is constant, therefore we know there's no change in the system. And the mass flow rate being constant means that m dot, let me write it in white, it means that m dot is equal to m dot 1 is equal to m dot 2. We know this from the fact that mass is conserved. There's no change in mass in the system. The system is steady. Therefore, the mass coming in has to come out. Okay? And the control volume stays the same size. Okay, so that's our first term in the equation. Our second term, so this isn't a part, just to write it down. And our second term in the equation is plus whatever is coming out, whatever momentum is coming out, so the momentum flux out minus the momentum flux in. And so that is plus m dot 2 out times v2 minus m dot 1 out times v1. Now, for these two terms here, why was I able to write v1 and v2 and I didn't have to write v1 n? So v1 dot n and v2 dot n. The reason why is because we said that we have a uniform outlet flow. So what that means is that the flow is coming into our system at an angle of 90 degrees and is exiting at a right angle of 90 degrees of our flow. So that means that we're essentially looking at something that is exactly perpendicular to our surface in and our surface out. So that means that v1 cosine theta and v2 cosine theta are just, we can say they're normal to surface. And since they're normal to surface, we can just write v1 and v2. So that's why, because it's normal to surface. So now, even though we have angles, we don't really need to work out what the angle is doing. We just need to figure out what's happening in terms of our system, and it makes it very easy to work out. So we can go forward and say that the sum of the forces, so rewriting the whole equation, we have the sum of the forces is equal to rho 2 times A2 times velocity 2 multiplied by velocity 2 minus rho 1 A1 velocity 1 times velocity 1. And we can essentially say, since we know that the mass flow rate is coming in is equal to the mass flow rate coming out, we can just say that the sum of the forces is equal to m dot v2 minus v1. Okay, so it's actually a very simple system, and we've come up with an equation for the sum of the forces. And we know that v2 and v1 are the velocities coming in and out at perpendicular to the surface in which they're coming in. They're normal to the surface. Okay, that's very important. So our final expression is the sum of forces is equal to m dot times v2 minus v1. Now, you can do this problem in a different way. So if we look at the vector diagram that they used, you can actually draw a vector diagram of what's happening. So you know that the velocity 1 coming in times m dot creates a certain vector up. We know that m dot times v2 creates a certain vector to the right. Therefore, the sum of the forces can be computed by joining the ends of those two vectors together by using a vector technique. But I think it's easier to use just the general equation and solve from the general equation and just solve it that way. Okay, it makes it a little bit easier to understand what's happening. So we can also express it in a vector relation, but essentially what the force needs to do is balance the change in momentum of the fluid. So we can say, as a conclusion, we can say that from our vector diagram, we can conclude that force needs to balance the change in linear momentum of the fluid as it turns in the tube. So that's why the force is to the bottom left, essentially. Our momentum is towards the top right, and our force needs to balance the change in linear momentum. So it's the force on the system required for the system not to move, essentially. Okay? So we're going to do another example problem, example 3.9, which I think is a better way of understanding this and is a little bit more complex. So we're going to look at this example, and then we'll stop after this. Okay, so example 3.9, I'm going to copy over the diagram once again. And in example 3.9, we have a water jet that we're going to analyze using linear momentum relations. So we have a water jet. Let me copy over the diagram as well, so that we have a better idea of what's happening. Okay, so we're told in example 3.9 that we have a water jet of velocity Vj impinges normal to a flat plate that moves to the right at a velocity Vc, as shown in figure 3.9a. So figure 3.9a is given right there. Now, it says, find the force required to move the plate, to keep the plate moving at a constant velocity if the jet density is 1,000 kilograms per meters cubed, the jet area is 3 centimeters squared, and Vj and Vc are 20 and 15 meters per second respectively. Neglect the weight of the jet and the plate and assume the flow with respect to the moving plate with the jets splitting into an equal upward and downward half jet. So essentially, we have a lot of assumptions and we have a lot of statements within this problem, and it's going to make it pretty complex, but hopefully we can solve it. So the first thing we can do is write out some of the assumptions and sort of make a diagram of what's happening. So the first thing I want to do is to sort of try and understand this problem. So we know that the first statement that was made, and just to zoom into this for a second, the first statement that was made is that Vc is equal to 15 meters per second. Okay, so we know that the velocity of C is 15 meters per second. And what that means is our control surface in this type of problem is actually going to be looking, so our control surface is going to be moving at a speed of 15 meters per second. So we actually have, as our first assumption, we have that our CS will move with the plate. So now we have a more complex problem where we have our control surface moving and not just a stationary problem. We could look at the system with a control surface not moving, but then our cart would essentially move out of the control surface and we wouldn't be able to solve anything in the problem. We're also told that Vj is equal to 20 meters per second. So Vj is equal to 20 meters per second. So this velocity here is equal to 20 meters per second. So the velocity out of the jet is actually higher than the velocity of the cart moving. So the cart moves at 15 meters per second. The jet has water coming out at 20 meters per second. So the other things we can write here is that we're told in the question that once the water hits the plate, it's divided into two different channels going up and down at 90 degrees. So we're told in the question that we can assume steady flow with respect to the moving plate with the jet splitting into an equal upward and downward half jet. So we're just going to assume that these jets are moving 90 degrees down and 90 degrees up. Okay, the diagram shows you sort of it splitting, but we're just going to show it in a very simple manner. Okay, so that's the assumption. So what is the velocity coming in to our system? So if we have our system here, what is the velocity coming into here relative to our control system, to our control surface, sorry? It's 20 minus 15. So it's actually 5 meters per second. The water is coming into our control surface at 5 meters per second. So now what we can do is we can focus on our control surface and look at what's happening. Some of the other assumptions we can make is that we have steady flow. We're told in the question we have steady flow. So we're going to assume that we have steady flow. And we're going to assume that we have 1D flow as well. Okay, just to make our problem simpler, we can assume 1D flow. And we can also neglect weight, which is given in the question. So we neglect weight so that we don't have an effect of gravity on momentum. It makes it easier in the first calculation. So we neglect the weight of the jet and the plate. Okay, so those are some of the assumptions we can make. And we can make more assumptions as we go along, but let's try and figure out what's happening. Okay, so now what we're going to do is we're going to draw a free body diagram of what is happening inside the control surface. So I'm going to zoom out again to 100%, just so the nodes stay at the same size. And what we're going to do is we're going to keep our diagram there, but we're going to zoom in to our control surface. So I'm going to draw my control surface, and I know that my control surface, we're going to use a coordinate system with y in the up direction and x in the sideways horizontal direction, okay? And we know that this is a moving control surface or moving control volume problem. And so what we're going to do is describe the problem as much as we can. So we know that we have a velocity c of our control volume, which is equal to 15 meters per second. We know this and we already wrote it down. Now, the other parts of the system, in green, I'm going to draw from the middle the solid plate where the water is hitting. Okay, so this is our solid plate. And we know that our water flow is going to be shown by our white line, essentially. So the water, what's going to happen is we're going to have water coming in from a jet here. And we don't care about anything outside of the surface, so we're just going to do water is coming in with a jet, and it's hitting this surface and going up and going down. Okay, so we have water coming in like this, and it's going up like this and going down like this. That's what our jet looks like in the most simple way. Now, we know that we're going to call this point J, okay, because we have everything in terms of the jet. So this is the jet, okay, so we're going to call this point J, and we're going to say that there's an area J where our fluid is coming in. And our fluid is coming into this area J at a velocity J, at a velocity of what? So our velocity is going to be equal to 5 meters per second. Okay, because our control surface is moving at 15 meters per second, our velocity is actually going to be equal to 5 meters per second. Okay, that's really important to know. So our velocity coming in is essentially equal to Vj minus Vc. Okay, that's our relative velocity coming in, which is 5 meters per second. And some of the other information we have is that the flow splits in half. So that means that if the flow splits in half, the flow coming out of here is going to have, so we'll call this 0.1 and we'll call this 0.2. We know that the area 1 is going to be equal to Aj divided by 2. The flow is split in 2. So Aj divided by 2. And the flow at the bottom, A2, is also going to be Aj over 2. Okay, so now we have a better understanding of what our diagram looks like and what is coming in and coming out of our system. And now, what we're going to be able to do is to come up with an expression for our momentum. So let's look at our system. What is being asked? So it's being asked that find the force required to keep the plate moving at a constant velocity. So the idea is to try and figure out how we can keep the plate moving at this constant velocity without creating a problem. And so what we're going to do is we're going to find the force required, essentially. And the first step we're going to take is to do a mass balance. So we're going to have to do a mass balance, just like in our previous problem, as well as a linear momentum balance. So let's start with our mass balance. And remember, a mass balance is just like equating the mass flow rates. So we know that the flow is steady. And since the flow is steady, whenever the flow is steady, we can say that the mass flow rate out is equal to the mass flow rate in. And we know that our mass flow rate out is equal to 0.1 and 0.2. So it's rho 1 A1 V1 plus rho 2 A2 V2. And that's equal to our mass flow rate in. Our mass flow rate into our control volume is from the other side and is with J. So it's rho J times AJ times VJ minus VC. That's our velocity coming into our control. Now, we also know that A1 is equal to A2, which is equal to AJ divided by 2. And we're also going to assume water is incompressible. If we assume water is incompressible, we're going to say rho 1 is equal to rho 2 is equal to just rho J. Our rho's are going to be constant throughout. Okay, so we can rewrite the above equation. And if we have rho's all equal to each other, we can cancel all the rho's from our equation. So we can simplify our equation to 1/2 times AJ. So I'm going to write everything in terms of AJ multiplied by V1 plus 1/2 times AJ multiplied by V2 is equal to AJ times VJ minus VC. Okay, and we can now simplify it by canceling AJ and not the 1/2, but all the AJs essentially, because they're all the same. So we can cancel them out from the equation. And so we're left with an equation that says that V1 plus V2 is equal to 2 times VJ minus VC. So we can see how much we can get done by just using a mass balance equation. And we can actually go even further than this. We know that the system is symmetrical. Our system is symmetrical, and therefore we can say that V1 is equal to V2. Okay, we agree that velocity 1 is equal to V2. Therefore, we can say that 2V1 is equal to 2 times VJ minus VC. And if we plug in the values, we get rid of the 2's, we just have V1 is equal to 20 minus 15. So V1 is equal to 5 meters per second. And that means that V2 is also equal to 5 meters per second. Now, we use the conservation of mass to do all this findings, and we always start from conservation of mass to find this. Now, logically, if you are thinking about the problem by yourself, if you have a velocity of a jet coming in at 5 meters per second, and you have no losses, and the flow splits in two and moves up and down, and the area is cut in half, it makes sense that the velocity stays constant throughout the up and down motion. Okay, so it makes sense that the velocity stays constant if there's no change in density and the area is halved on top and on the bottom. Okay, but you still have to go through the mathematics to make sure that that's correct. So it's just the mathematics helping us solve a problem that we could have maybe deduced from experience, but it's better to have the math to back it up. Okay, so now that we've done mass conservation, we figured out a velocity. we now have some more information about the problem, and that's good, because with this more information, we're going to be able to go further into the problem. Now, let's use now a linear momentum equation to solve for the forces, or to find forces. So if we use linear momentum to find forces, what we can do is we can say that our axis is going to be y and x. We're going to call them y and x. And remember, we can either do a sum of the forces in all the directions at once, or we can separate them into the x, the y, and the z direction. Now, in the z direction, we have no movement, so we don't really need to work it out. But we should solve our problem in the x direction and solve our problem in the y direction. We want to try and find our, essentially, the force required to keep the same velocity, in the x direction and in the y direction. So we're going to have two different forces. We're going to call these forces reaction force x and reaction force y. Hence why we drew in the diagram Rx and Ry. Okay, I was a little bit ahead of myself, but essentially we're going to be looking at what the reaction force in the y direction is and what the reaction force in the x direction is based on the system in order to keep the system at the same velocity. So we can say that the sum of the forces in the x direction should be equal to the reaction force in the x direction. Okay, we know that it should be equal to the reaction force in order to keep a balance. And that reaction force is going to be equal to the velocities, to the momentum flux created by the velocities. Okay, so the linear momentum equation, since we have a steady system, therefore we can get rid of the time term, the complicated time term in our original derivation. So we're left with just terms of momentum flux being applied to the system. So we're going to look at the momentum flux in minus the momentum flux out minus the momentum flux in. So we're going to have that the sum of the forces in x is just equal to m dot 1 u1 plus m dot 2 u2 minus m dot j uj. And remember, u is just the x component of velocity. So it's the same thing as saying vx. Okay, we just use u as a replacement, so it's just u. So we now have these three terms. Now, if we look at our free body diagram, do u1 and u2 have a term? So the velocity coming out at point 1 and point 2 is vertical. So what does u1 and u2 equal to? u1 and u2 have no component in the x direction. So u1 is equal to 0 and u2 is equal to 0. And uj, which itself is actually moving in the x direction, so uj is moving in the x direction, would just be vj minus vc. Everything is moving in the x direction for the j entrance. So we have vj minus vc. So if we simplify this equation, we now have the reaction in x is going to be equal to the force created by the jet, essentially. If we can keep the reaction force with x in accord with the force created by the jet, then we can keep the constant velocity. So we have that so we have Rx is equal to minus m dot j times uj, which is equal to, if we write down what the mass flow rate is minus, I'll write it like this, so rho j multiplied by aj multiplied by vj minus vc times vj minus vc. Okay, so remember that within the mass flow rate term, mass flow rate in the x direction is equal to rho in the x direction. So rho a in the x direction. I'll keep it in the x direction just to, it's a for the area in the x direction multiplied by u. Okay, so we have 2 times u in the equation because we have 1 u inside the bracket and 1 u outside of the bracket. So we're left with minus 1,000 times 0.0003, and that 0.0003 comes from our initial question. We're given that the jet area is 3 centimeters squared. So this is 3 centimeters squared in meters squared. Okay, and the 1,000 is also given in the question. It's kilograms per meters cubed, telling you the jet density. And then we multiply this by the velocity, which is 5 squared. So we get that this is equal to minus 7.5 newtons. So in order to keep the velocity the same and to keep everything steady, our reaction in x, our reaction force on the system would have to be equal to minus 7.5. So what does that mean? That means if we go back to our diagram, in order to keep our control surface and our whole system moving, we're essentially applying a reaction force in x, which is equal to minus 7.5 newtons. So we assumed initially that the reaction in x would be towards the right. So because of the negative, it gets flipped towards the left. Okay, so it just means that the reaction force is in the negative x direction. So we have y and x. Therefore, our reaction force is in this direction. Okay, and that reaction force is going to allow us to keep the same velocity. If we had no reaction force, the velocity would keep increasing because we would just have the jet pushing on the system and no reaction from the system. Okay, so now let's look at the sum of the forces in y and try and find the reaction in the y direction. So if we look at the sum of the forces in the y direction, we have that they're equal to reaction in y. So we're going to say reaction in y is whatever's happening in the y direction to counteract the system. And we know that there's no term with change in time because we have steady flow. So we can say that Ry is equal to m1 v1 plus m dot 2 v2 minus m dot j vj. And we know that our system looks something like this. Okay, so we have flow coming in, which is vj, and then we have v1 and v2. We know that vj doesn't have any component in, we have no component of vj in the y direction, so vj is equal to 0. So this term goes to 0 because there's no component of the jet in the y direction. So we're left with v1, which is going to be equal to velocity 1. And v2 is going to be equal to minus velocity 2. Okay, remember that we're looking at a sum of forces in the y direction. The force has to have direction. So the velocity also has direction. So v2 is actually a negative term. Okay, so we have that ry, because it's going in the opposite direction. So we have ry is equal to m dot 1 times v1 plus m dot 2 times minus v2. And we also know that v1 is equal to v2. So if we substitute v1 for v2 in here, we get that ry is actually equal to 0. And it makes sense. If you look at our system, if we look back at our system, there's half the flow going up, half the flow going down. So the forces in y on our system are pretty much equal to 0. They cancel each other out. So we could have, again, from deduction, said that the reaction force in y would be 0. But we still have to make sure that we understand what's happening. So we get that the reaction in y is 0 newtons. So our final solution says that the reaction in y is 0 newtons, and the reaction in the x direction is minus 7.5 newtons. And this is our final answer for the problem. Okay, I hope this makes sense. And we're going to continue our discussion of momentum as well as a special case of the momentum equation in video 3. So we'll see you in video 3 for that.